Maybe I'll try to do that. I'll start here. So thank you all for coming. I'll try to make this short since I'm very much looking forward to your talks. As Matthias was saying, when we initially started planning this workshop, we had this idea of making it not just an event for, say, core quantum information personnel, but like to invite people from neighboring areas or neighboring fields who are interested in quantum marginals or reduced density matrices in specific, but also in the techniques that we use when we compute with these objects. Say, thank you. And so naturally, if I asked any two of you, your backgrounds might be quite varied. For instance, and maybe you can, as Matthias was saying, maybe you have different research interests. And so what I wanted to do basically is what we wanted to do with this empty slot now was to give them, say, an interactive kind of program overview, where we will go through this week's program and explain kind of how it is all connected. And I would also like to take the opportunity to recall some basic notions which most probably you're familiar with, such as the notion of a quantum marginal. And so that in your talks, when you give your talk, you can rely on everyone knowing what reduced density matrix is. So with this, maybe let me start. So also some kind of mindwork. So this will be created on this blackboard. So the subject of this talk is quantum marginals. Or reduced density matrices, which is their more mundane name, if you like. So let me once and for all just say for the maybe less physically oriented among you, recall what a reduced density matrix is. So what this object is that we care about in this workshop. And so let's start with that. So a state of a quantum system, of course, is described. A quantum system itself is described partially by a Hilbert space, where and so the state of the system then is given by a density matrix or density operators, and of course to some different operate on this Hilbert space. As many of you know, so I will take the quantum system. I find an operator. It should be positive, it should have a unit trace, and it should act on some Hilbert space. Now, suppose you had a system which is composed of many different subsystems, and for each subsystem you know the Hilbert space that describes the subsystem. And one of the axioms of quantum mechanics tells you that the Hilbert space to use to describe your entire system is simply the tensor product of the local ones, at least of the particles that we look at are distinguishable particles, and we'll come to revisit this issue in a bit. So, composite systems. Distinguishable particles are described by the tensor product Hilbert space. So if I have, say, two particles A and B with associated Hilbert space H A and H B, then the overall Hilbert space would just be the tensor product. Now suppose that you have such a, say, a two-component system. Of course, it's generalized now to many particles. I can just take, it should give you a tensor product with more factors than just two. So suppose we have such a quantum system, it has two parts. Now, what I said before, its state should be described by a density matrix, a density operator. So this operator is called a density matrix. E matrix. So now we know that the overall state of the system is described by a density matrix, which I will call rho AB, because my system has two parts, A and B. Now you could ask, well, suppose I'm just interested in one of the systems, say system A. What is the description of it? Then there should also be a density matrix, so positive operator of unit trace, describing the state of the subsystem. And this is the reduced density matrix. I will now define it mathematically, so that, you know, if you don't care so much about physics, you have a formula that you can compute with. So if rho AB is the quantum state of the composite system, then state of, say, subsystem A described by the so-called reduced density matrix, or the quantum marginal. Reduced density matrix. Which is usually denoted just by rho A, if rho A is the overall one. And it's defined by the following relation. Namely, it is the unique matrix such that if you take an Hermitian operator XA and you compute the trace of rho A times XA, and this should be the same as the trace of rho AB times XA times of the identity on the B system. Trace is non-degenerate form, so there exists a unique such matrix such that this holds for all XA. And usually we just take these to be Hermitian operators. So in quantum physics, this is a very natural interpretation. Because this trace, so these Hermitian operators XA are called observables. They represent observable quantities of your quantum system. And the trace of the state times the observable is the expectation value of that observable. So basically this is saying that the expectation value of an observable only living on the A system is given by the expectation value of the observable when you tensor to the identity on the B system if you evaluate it on the overall state. Right? And so I could also write this down in coordinates, but maybe I will not. So the map sending rho AB to rho A is also called the partial trace. Trace, and of course this makes sense for not just density matrices but for arbitrary operators on this bipartite system. Yes, for arbitrary operators on this tensor product Hilbert space. Now, suppose you start out with some initial state, say rho AB, and you compute the reduced density matrix rho A and rho B. Then surely you could ask, what is the relation between these two reduced density matrices? Like, are there any constraints can you choose them totally arbitrarily? Actually, in this example, you can. Or are there any connections, you know, or maybe you have some additional knowledge about the overall state, and for instance, you have some knowledge about the rank of this of the overall density matrix. Then you could ask, what are the corresponding constraints on rho A and on rho B? And this, if you like, is a basic problem that you can even study purely out of mathematical curiosity, I would say, called the quantum marginal problem. And this, which is also what Alexander Kjashko was interested in, who should have originally filled this spot or given this lecture. So the marginal problem is basically the following problem. Suppose you have not just two particles but many particles. So you have some Hilbert space, which is a tensor product of many factors, H1, Hn. And so before I was saying I have an overall state, and I look at the marginals and ask what is the relation. I could turn this question around and ask, suppose I give you density matrices for subsets of the particles. for instance, suppose I had 3 particles, 1, 2, and 3. And I would give you density matrix for H1 tensor H2, another one for H1 tensor H3, and a third one for H2 tensor H3. So row 1, 3, row 2, 3, row 1, 2. And I could ask, is there an overall state whose reduced density matrices are given by these prescribed ones? So more generally, I could be given density matrices on some subset of the Hilbert spaces H. For some subsets I of all particles, not for all of them, for some subsystems, are they compatible? So does there exist a global state giving rise to these marginals? So this is the Marshall problem. And there's many, say, special cases or instances of this problem which are of interest and which have been studied, and I want to in particular focus on 2 of them. One is the, like the most basic of this, most basic version of this problem, if you like, is if you're given. Maybe I should say something about this problem I do here first. So evidently, one necessary condition for there to exist a global state is that if you compute the reduced density matrix of the one system for this one and for that one, then they should better be equal, right? Because otherwise, the problem would be ill-posed from the start. But this is not a necessary condition, so I should say that. So this is a difficult problem in general to find this out. And it is actually, now you could ask, is it still a difficult problem if instead of 2 body reduced density matrices, so density matrices of 2 particles, I'm only giving you 1 body reduced density matrices. So suppose I give you row 1 to row n and ask, does there exist a global state? Then this is kind of trivial, right? Because you could just take the tensor product of all of them, and you're done. Now if you apply this partial trace operation, actually because these are tensor products, what you do is just you take the trace of these individual factors. So clearly this is a quantum state whose reduced density matrices are given by row 1 up to row n. And it's also clear that this recipe doesn't work anymore for this situation because we have these overlaps. Okay. So this is somewhat easy, but you could ask the following version: what if you control something about the overall state? For instance, you could ask that the overall density matrix should be rank 1. Which is a natural constraint from the point of view of quantum mechanics. What if it is a pure state? Or more generally, what if the spectrum of the overall state, so the eigenvalues, are fixed? And this is one of the contributions of Alexander Kerschke. He gave an algebraic solution to this problem. Using algebraic geometry, geometric invariant theory, and so kind of, sort of difficult mathematical tools. We're happy that so I was mentioning these 2 fields, in mathematics, which are kind of intimately connected. So algebraic geometry and representation theory. So maybe I should add them to this little mind map over here. So maybe I should understand between them because they're so connected. And so what I was saying is basically in the special case of the quantum margin problem, this one-body quantum margin problem has actually been solved not by, say, standard methods that are known to like that are standard in quantum physics, but by methods from, algebraic geometry, symplectic geometry, representation theory, in particular by something that is called geometric invariant theory. And so we're very happy that we could convince some few mathematicians as well to come to this program to give us talks about precisely these mathematical topics. So I guess that would be maybe one of the more unexpected connections from the title of the workshop for the program. So in particular we have Brand Durand from ETH Zürich, Nicolas Resser, and Michel Gagne. So of course I will. So what I will do is, I will put your names above boxes. You might of course disagree with my choice of box. Please don't take it personal. It's probably due to my bad judgment that I put you above one box or the other. So for instance, what Nicolas Resser did, he kind of gave sort of a, like a kind of a more tight solution of this problem, if you like. For more general class of problems, but so there's all these connections. Now maybe I should also write down that on the side of representation theory, there's an object that you might have heard of called the Kronecker coefficients, which are kind of group theoretical or representation theoretical objects that also guide the solution of this problem. So this is maybe also unexpected, and I will not be able to explain this now, but I think we will come back to this. Now there's one thing I wanted to mention for the benefit of those of you who come from this area. So there's one closely related problem which is very well known in mathematics, which is I guess the problem of resolving Horn's conjecture, or problem by two Weil, as I understand originally.
Yes, it's Weil's problem.
Is it Weil's problem but Horn's conjecture? Is that right?
Horn conjectured
as the solution.
Horn conjectured a solution.
That's right.
And Koyachko solved Weil's problem, and his solution was different from Horn's conjecture.
All right.
And only later, when Knudsen and Powell worked on it, they showed that if both sets of inequalities were redundant, and when they reduced the redundancies, they reduced to the same set. But the problem came from Weil in 1912, and that's what Koyachko solved.
Thank you. Okay. So I should write Weil's problems. So this problem by Weil is it's a little easier to say than this Montemarchi problem. It's about, you have three Hermitian matrices A, B, and their sum, and you ask what are the constraints between the eigenvalues of A, the eigenvalues of B, and the eigenvalues of A plus B. And it kind of has a similar flavor, although I didn't quite maybe tell you why. So in this case, we also fix eigenvalues, right? So we fix eigenvalues for the overall state, and from this overall state, you get the reduced density matrices. We can look at the eigenvalues. We can ask when are these compatible. Similarly, here we start out with two matrices A and B. Now, instead of tracing out, we form their sum. And we can again ask what is the relation between the eigenvalues of this guy and the original eigenvalues that we started with. So it's kind of structurally similar, and also the methods to solve this problem are rooted in, yes.
The statement is more like when you start out with the quantum marginals. You start out with three sequences A, B, and C, and ask when there are matrices for which these are their eigenvalues.
And such that the sum is zero, for instance, or
the sum of
that
A
they sum
plus
up
B.
to. That's right. Yes.
And so it's more of the reverse problem.
Yes.
I mean, they're equivalent, but
Right. So like morally speaking, that's true. Okay. At any rate, so this I should write down Horn's conjecture. Just write down Horn's name. So again, this ties into this, these two boxes. Now, one physical motivation for studying this problem comes from quantum chemistry. So let me try to explain this. And it is actually if you like an instance of this above problem. Now, when you require the overall state not to be just any density matrix, but a density matrix of a fermionic system. So fermions are indistinguishable particles. If you have n fermions of the same kind, then all these Hilbert spaces H1 to Hn are the same. But in addition, not just any density matrix is good, and is an appropriate description of your of your quantum state, but you want density matrices that are supported on the antisymmetric subspace of a tensor pair only. So, fermions, you would look at, I guess, the antisymmetric subspace of some tensor pair, H tensor n, and you would ask that your solution to the problem, so your overall state, should actually be only supported on this antisymmetric subspace, which makes the problem much more complicated. In fact, there's already now constraints on the single body level, on the level of the rho ones. For instance, the famous Pauli principle, about which we will hear more, I think, at this conference. So kind of the idea behind Pauli principles in very vague terms is, I guess, because you're on this antisymmetric subspace. If you exchange any two of the electrons that you cannot distinguish, you should pick up a factor of -1 of the antisymmetry. So if they're in the same state, but if they were in the same state, then if you were exchange, nothing would happen. So that cannot be. So this is, this is of course very hand wavy. In mathematical terms, I think you can describe it as follows. You can say that if you normalize these reduced density matrices as I did before, if you define it as additive, then the eigenvalues of, for instance, the one-body reduced density matrix, and I should say that all these are equal because of the permutation symmetry or antisymmetry, then the eigenvalues of this one-body reduced density matrix are all between 0 and 1 over n. So maybe I should write it like this: spec rho 1 over n. Whereas originally, when I defined what a density matrix is, I was just saying it should be a positive operator of unit trace. So a priori, I only know that the eigenvalues should be between 0 and 1, but here there's a tighter constraint. And if you require additional things about your overall state, then, for instance, that the state should be pure, then there's actually there's many more constraints. And again, this is a variant of this original problem. In mathematical terms, we look at a different representation, if you like, so that we get different. It's maybe no longer the Connect coefficients, but other kinds of representation theoretic coefficients that guide the solution of this problem. Now, one of the motivations, maybe I should add a little box here. One of the motivations actually to study this version of the problem comes from quantum chemistry. Fermions are, say, the electrons surrounding some atom or molecule. So maybe I should write chemistry here. And I should say that the problem in this case is called the n-stability problem. Because essentially, there's this parameter n left. So n-stability, you're given say one body, or more interestingly, a two-body density matrix. You ask, does there exist an extension? Does there exist an overall state on n bodies whose marginal distributions are the given ones? So this is called the stability problem. So this is just the fermionic version of this quantum marginal problem that I introduced before. And so the original motivation, I think, was to compute ground state energies, kind of a new approach to computing ground state energies physically of Hamiltonians that are relevant in quantum chemistry. So let me maybe try to sketch this. So the idea is, I said before that a physical system is described by a Hilbert space. Then I was struggling a bit because I didn't want to talk about Hamiltonians at that point. Usually there's always also a Hamiltonian attached to the system. It describes the time evolution, the dynamics of your quantum system. And Hamiltonian is not just a self-adjoint operator, it's another observable. It's just a self-adjoint operator on your Hilbert space. And for instance, the expectation value of the Hamiltonian is then the energy of the system in a certain quantum state. So in Hamiltonian set of conjecturing quantum chemistry, actually it makes sense to, in the context of quantum chemistry, it makes sense to look at Hamiltonians that are not fully general matrices on this Hilbert space over here, in this Hn, but rather which have a specific form. For instance, they are Hamiltonians that where basically which are sums of terms, and in each term, only two of the particles really interact. So they are two local Hamiltonians, I would say. So let me try to write this down in like without using slang notation. So basically, what I will do is I will just I will sketch kind of an ansatz for an Hamiltonian. I want you to trust me that this is maybe a useful one to make. So what I want to have is I want to build this Hamiltonian on n particles from a Hamiltonian. From a smaller Hamiltonian which only acts in two particles at once. So this is my little h. And I give this little h two indices, basically saying that one of the factors should be the ith tensor power, the other one should be the jth tensor power. Then I just do the identity on all other systems. So identity on the first system. I omit the ith one, I omit the jth one, the nth one. And I want these hij's to be all the same Hamiltonian. So this is a permutation symmetric model, and I guess it makes sense that it's permutation symmetric since we have these distinction particles. So now if I have this permutation symmetric Hamiltonian, I can restrict it to this antisymmetric subspace. I get an operator on the antisymmetric subspace. And for fun, I will also normalize this by n choose 2. So the number of such pairs ij. Usually you'll probably see this, if you're a physicist, you probably like to write this down in second quantization, maybe. But on the other hand, if you would like to write this down in second quantization, you maybe don't need my explanation, so I will maybe not do this for now, but I will leave it in this form. So I was saying that the energy of a given quantum state.
Excuse me, I cannot read. Can you explain? You have Hij, tensor, and what is it?
Yeah, okay, so I should be more precise. So basically what I mean is the identity operator on all the tensor factors apart from the I and the jth one.
Okay.
So I put these little
I can't, it's not legible for me.
It's like backslash v, not
Maybe a bit bigger.
maybe I
Just
should.
say the identity on
Okay.
the count.
Maybe I can
Okay, now I see.
on the case system.
Thanks. Okay.
Maybe that's right.
Okay.
It's like okay, identity, so everything but the I and the j.
I guess there are lights you can turn on. There, spots.
It might be also, I don't know.
Maybe. The very small indices are difficult to read.
Yes,
A little bit,
I can try to write them bigger, but I don't actually know where the light switch is, so maybe someone hears me
Where is spot?
in this back office.
I don't know.
I don't know, sorry. Thanks. Thank you. Sorry, not bad.
If you like just for there's a special light for the Blacksburg.
This is good, no? It's much better.
Are you happy?
That's all the light you have. So I
Just
think
me,
the
that's
solution
like
is to write larger.
Okay, I will. So this. Something is happening. Okay, so I want these to be all identical little h's, but when I write down this index I and j, I want them to act on the ith and the jth vector of the Hilbert space, then I have identities and everything else. This is the kind of ansatz of a Hamiltonian that I want to look at. Now I was saying before that the expectation value of a quantum state rho, maybe I should write rho n, and hn, is the expected energy of a quantum state with respect to this Hamiltonian. And so the minimal possible energy, which is just the minimal eigenvalue of this operator h, is what I would get by minimizing all rho n. This is what we call the ground state energy. And so minimizing of all rho n, I really mean I minimize of all density operators, that will all our density matrices on the fermionic Hilbert space. 20 power. And I said this before, but maybe I should write this down. I was saying before that all, say, k body reduced density matrices, so all reduced density matrices of k of the n particles, they're all the same because of the permutation symmetry. So all k body marginals or reduced density matrices are the same. And I will denote them by rho k. Where k is, how many guys are left. So for instance, I could choose rho k just to be rho 1 to k, my previous notation. And rho n is rho n in particular is the global state. And now the idea is the following. So this Hamiltonian is a sum of terms, and in each term I basically have a huge identity tensor summing which only acts on two particles. And so from my very definition of the reduced density matrix from the beginning, I see that whenever I have identities, I can get rid of these identities and replace the overall quantum state by the reduced density matrix. So instead of evaluating, like if I had the sum I smaller than j, I have the expectation value of hij tensor identity in the state rho n, I can replace this by the expectation value of the little h in rho ij, if you like. But all the rho ij's are the same, they are just the same, equal to the two-body reduced density matrix. So I get a sum of, n choose two equal terms, so I cancel this here, and what I end up with is the following. Trace little h, rho 2.
And hij itself is permutation symmetric.
That's a good point. Why not? Yes.
H12 rho 12.
Yes. I mean, exactly. It's like H12 rho 12, and so yes. And so maybe I should, maybe I should be use the notation from like this. Or I can use the new notation where I suppress these indices and replace them by superscripts and just write H. Now this seems like an enormously clever idea because I started out with a minimization problem over huge space, over all density operators on this big antisymmetric Hilbert space, and I cut it down to minimization over only two-body operators. So over density operators on only two particles, which is a much smaller space. Trouble is that when we went from here to there, what we did, we were replacing this n particle state by its two-body reduced density matrix. But not all two-body reduced density matrices actually come from an n-particle state. So I think this was the original motivation to studying this problem. No, that is right.
Yeah, I mean, people even published papers in which they got too low an energy.
That's right, because because it's a minimization problem, and if you minimize over too much, you get too small numbers, right? So you should only optimize over rho 2s, that are quantum marginals, that are reduced density matrices. Which is actually a difficult problem, and it is even difficult in a computational sense. So it has been shown that actually characterizing this set is not only NP hard but QMA hard, which is like the quantum version. And in a sense, I think it is hard for this reason, because otherwise you could compute ground state energies of such low Hamiltonians that have, which has been proven a hard problem. So I think that's maybe also it's both the problem and the explanation, if you like.
The minimization itself is not that hard because it looks like semi-definite optimization. The problem is to
characterize.
Definition.
I mean, this.
Yeah, the problem is.
Let's detect the domain of definition. The minimization itself is not that.
Basically,
function.
I mean, this. So, so this problem is over a simple space, but it's a huge space. The space of all density operators on your n-fold n-particle Hilbert space. This is not optimization over a small space, but a complicated space, because it's kind of the image of this partial trace map. And so yes, and it is a hard problem actually to decide when such a given two-body reduced dense matrix does come from an n-particle state. So hard in this computation sense. And so maybe I should take the opportunity now to add another box to this blackboard. Computation complexity theory. Computation complexity. So, subfield of computer science where people study the computation complexity of problems, the complexity of computation problems. Like in theory, how efficient can you solve a problem? And so basically was saying that this n-reducibility problem, it has some connections to computation complexity. I mean, for applications, a very crucial connection. Maybe saying that maybe it's not so easy. Maybe this trick is not so clear if this trick can be made to work. But still, I mean, this is kind of a generic result. It's basically maybe saying that it's hard to program a computer which you feed this H and you get the ground state energy. But still, it could be that for specific models, maybe actually you could try to approximate this region, and maybe for specific models this does a very good job. And so I'm very happy that we will have a talk by Mauro Nakata about actually using this reduced density method to compute ground state energies and compare them with with other known results. We have one talk here. I should have mentioned Mary Nebraska's talk first. Actually, she has of course been interested for a long time in this problem, and she will tell us some new things about basically the uniqueness. I think the uniqueness of pre-match is like how many row n's are there for a given row 2. So that's my understanding. So then we also have Christian Schilling's talk, who's a fellow PhD student at ETH, who will talk about essentially the idea. It's also about fermionic systems, where one looks at the one-body reduced density matrix. I guess this would be another way to approximate row 2 by just enforcing the one-body quantum-marginal constraints. Finally, now I was talking about fermions. So there's a talk by Matthias.
I may change my talk.
Sorry?
I may change my talk.
Oh, you may change your talk.
Yeah.
Excellent.
We'll
I mean,
maybe there's a talk.
Okay, maybe there's a talk. I can speak letters. So there will be a talk about the title that I know of is like fermionic, or the power of fermionic noisy quantum computation. So it's a bit of a different flavor than maybe what I was talking about so far.
Yeah, but I may talk about Q&A, but we'll see.
Okay. Very good. So maybe I should speed up a tiny little bit so that we are not too late for the coffee break. So you see that there's still quite a bit of space left. So let me start filling this. There's some other applications. So besides quantum chemistry, we will also have a talk on the role of quantum marginals in quantum spin systems and condensed matter theory. By start. And if time permits, maybe I will talk a bit about the connection here as well. But now I want first to start a bit of a different discussion. So I kind of, I start with this n-reducibility and quantum marginal problem. I went from there and wrote down some boxes. Now I want to go in a different direction, in the direction of entropies. I was promising before that I would reduce the reduced density matrix so that you don't have to do it. I will also define the phenomenon entropy for quantum states so that you don't have to define it in your talk. So this is the entropy. Maybe I will motivate it in a I don't know, maybe in a somewhat unorthodox way. for the purpose of this discussion, of this program overview. So we can talk about entropies, and maybe I hope this is kind of readable over here. So the perspective that I want to take, I mean, before I said that the quantum state of the state of a quantum is described by such a density matrix, by positive operative unit trace. Now, the set of all density matrices, the set of quantum states, is a closed and convex set, right? If you mix two quantum states, you again get a density operator. Here the trace will be left the same. The positive matrices, they form a cone, so this is all well. It's closed and convex. And for the purposes of this discussion, let us also assume actually that the Hilbert space is finite dimensional. Now, in this case, you know by the spectral theorem that you can decompose any positive semi-net operator, and into its eigenspaces, or into projections on its eigenspaces times the eigenvalue. So what we can do is we can take some rho and decompose it as sum pk, capital pk, where these are, I could require them to be orthogonal projection operators. So they project onto the eigenspace, and pk is the eigenvalue. So this is by the spectral theorem. So, and now suppose that I'm working in a finite dimensional Hilbert space, so this will be a finite sum. I don't want to worry about any conversions, although of course one could make this to work. Now in general, these eigenspaces might be degenerate, but I can always split them up. I can always split up a rank 2 projector as a sum of rank 1 projectors. So I will assume that these capital PKs are rank 1 projectors, rank 1 projection operators. And so there might be, some PKs might occur multiple times. Like the identity over 2 would be a density operator on C2, and I could choose any two orthogonal projections with the same PK over E. Now, rank 1 projection operators are density matrices themselves, right? Because they are rank 1 and they're projection operators, so the eigenvalues are 0, 0, 0. That's a single one. They are positive, and so they are also quantum states, and we call them pure states in quantum physics. We call them pure states because they cannot be decomposed anymore in this way. It's called a pure state. And there is a certain notation that people will oftentimes use, namely, suppose that pk is a rank 1 projection. So a projection to a one-dimensional Hilbert space, a subspace, namely this, for instance, the subspace spanned by some vector psi k. You can ignore this cat if you like. So psi k is a vector in the Hilbert space. This is a one-dimensional subspace. Pk should be the projection operator onto the subspace. Then what people often write is, instead of pk, they write the following. So they take the vector using the Dirac cat notation and the corresponding dual. And so they use this notation. So just to also remind you of this one, if you like to use different notation. So these pure states are kind of the extreme points of this convex set of quantum states. And we saw that we can write any density matrix as a convex combination of pure states. Interestingly enough, these pure states, there's infinitely many of them, right? Kind of for all directions in the Hilbert space. Even if you had a two-level system, even suppose you had C2, and you ask about pure states there, so pure states would be directions in C2. So that would be complex projective space. The CP1, so the set of pure states, so there's a mathematical remark. Pure states are CP1. If you know CP1, then you know that CP1 is the same as the two-sphere. The two-sphere is what we like to call the Bloch sphere in this case. So there's a two-dimensional sphere. And the points on the sphere parameterize the direction, parameterize all the one-dimensional subspaces of the C2. And so these are the points on the surface of the sphere. And so it turns out that if you now if you take the convex hull of the sphere, of course you get the entire ball. So the sphere is not sphere. So what this says is that any point in the ball, whether on its surface or on the inside, corresponds to a density operator. And so this is kind of a like an indirect way or another way of seeing this from this perspective. Now, we could be interested in measuring how far a quantum state is away from being pure. And so one way of doing this is, well, I don't know, we could count the rank of this object. Another thing of doing is we could compute the entropy, and we could attach some numeric quantity which is 0 for rank 1 quantity and non-zero for things that are not rank 1 in some continuous way. For instance, if all the eigenvalues are equal, so they would have to be equal to 1 over the dimension of the Hilbert space in that case, so that the trace is 1, then this looks pretty mixed. And so maybe this quantity should be large. And so what we define as the Von-Neumann entropy. So you can think of the Von-Neumann entropy that we will now define as kind of measuring how far state is away from being pure. So the Von-Neumann entropy, I guess, this is totally impossible to use in English. So now I want to attach this numerical measure to any quantum state to basically tell me how impure it is. And the one I choose to use is the Neumann entropy. It's defined as follows. So it's S of some density matrix rho, and maybe I should have used rho A here because I called my Hilbert space, denoted my Hilbert space by HA. So I want to define this on an object minus trace rho A log rho A being the logarithm of this operator, or in hands-on terms as the sum of all k, dk log dk. I want to define 0 times log 0 by continuity to be equal to 0. So, log 0 defined to 0. And it's kind of easy to see, so because of this, if I have a pure state, then all the pKs are either 0, and there's a single one which is 1. So for the pKs that are 0, I get 0 by definition. For the case where pk is equal to 1, I get log 1, so again 0. So this object is equal to 0 precisely for pure state. So S of rho A plus 0 is the same as rho A is a pure state. That is the rank 1 projection. In general, this quantity will be non-negative, and it can also be bounded above by the logarithm of the dimension of the Hilbert space. If this is attained, then yeah, okay. Anyways, so starting now, the reason why I chose to use the entropy rather than some other measure for this impurity was basically because the entropy is of course a basic concept in quantum information theory, and you can use it for many things. You can use it to do quantum version of information theory, so quantum Shen theory. So maybe I should write down here. So in classical information theory, the entropy basically tells you, for instance, how well you can compress, and so on. So there's many like concrete tasks in quantum information theory, and it's kind of all rooted on Shannon's idea of the differential entropy. So this is kind of the quantum generalization. Now one can do quantum Shannon theory. One can do information theory, so coding, compression, and so on in Hilbert spaces rather than the ordinary probability distributions. And so we'll have some talks on that subject matter. Aram Harrow will give a talk on quantum, I think, connecting quantum Shannon theory and actual representation theory. There's a funny link over here. And also, as Matthias is saying in the introduction, Professor Holevo will will give this public lecture, I think, this evening on quantum mechanics theory in general. So we are very happy to have that talk. Now, regarding entropies, there's other entropy measures that people have been studying. So there's, I was saying, there's the phenomenal entropy, which is defined as follows. There's the Shannon entropy, which is defined as follows, as here. But there's also other entropy measures. There's classical entropies for quantum states. I guess there's no quantum entropies for classical states. And so Jan-Philipp Soderberg will give a talk about a different entropy, but nevertheless, like one that is connected to this topic. And I think this will be the first talk this morning, after I'm done with this pretty soon. Maybe I should close with one last subject, namely, one last thing that I want to, maybe actually two things I want to point out. First observation is the following. Suppose you have I defined the entropy for a quantum state without making reference to any subsystems or so. But suppose you had a quantum state, say rho ABC of 3 particles. Then you could compute the entropy not only of the overall state, but also of the reduced density matrix. And you could ask, what are the relations? What are the constraints? And again, this is kind of a quantum algebra problem, right? Because ultimately, such relations and constraints constrain the solutions of this quantum algebra problem. They constrain, they give conditions on when our reduced density matrix is compatible with the overall state and with each other. So you have entropy inequalities, for instance, the famous strong subjectivity entropy inequality. Maybe let me just indicate this by saying, from this state you can compute many entropies, SA, FA, and so on, where I define SA as the entropy of the reduced density matrix for particle A, for particle A and B, so this is the entropy of rho AB, and so on. And they are not all independent. Then there's one last connection I want to talk about is about entanglement, and I want to talk about entanglement in the very very basic sense. Kind of like the motivating example for maybe finding the name, if you like. And it's the following observation. It is not true in quantum mechanics that if you have a pure state, a globally pure state, rho AB, the pure state again was a rank 1 projector, and we use this funny notation, cat psi AB, bra psi AB, to be noted. And it is not true in general that the reduced density matrix is also pure. Now, why should this be curious? It should be. It's a curious phenomenon because if you think of classical probability theory, then in that case, the counterpart of the pure states are deterministic distributions. So suppose you have collective random variables, you know the value of each of them. Then, of course, if you forget about some random variables, you still perfectly know the value of the remaining ones. So classically, marginals of pure states are pure states. Quantumly, this is no longer so. And there's a famous example that I'm maybe write down of a bell pair. So this is I will write down the vector Hilbert space. So 0 is just one orthonormal basis vector. 1 is another orthonormal basis vector. And so this state, it's by definition, it's a pure state because the projection onto this ray, onto this vector Hilbert space. But if one goes about computing the reduced density matrices, one easily sees that this is 1/2 times the identity matrix. So this is a state in C2 times C2. And I should have done this right at the beginning as an example of the definition. If one computes the reduced density matrix by the formula that I gave before, and then this is a rank 2 operator on C2. Very well. So we have this funny phenomenon, and this is what we call entanglement. Maybe I will not write this down here, but I will write this down today rather. So this is basically the original phenomenon of entanglement from a mathematical perspective. And another way to say it is basically this phenomenon will occur whenever your vector is not a tensor product. In the case of pure states. So recall that I looked at pure states only. So for pure states, basically the state is entangled if it is not a tensor product. Psi A tensor psi B. Very well. So another way, I guess, to say it. So now we have this. But now, now I said that a quantum state is entangled if the reduced density matrix is not pure, but now we have a measure, right, for measuring a purity, which is this von Neumann entropy. So what we could just do is we could, well, I guess we could, for a given pure state, define a quantity psi AB, which is just the von Neumann entropy of the reduced density matrix rho A. This is called, I think, the entropy of entanglement. It is zero if the state is a product state, otherwise it is non-zero, and the larger it is, kind of the more entangled your quantum state is. If it is maximal, then we maybe would say that the quantum state is maximally entangled and so forth. So kind of you can use entropies to measure entanglement. I mean, there's of course much more to entanglement. Instead of looking at the entropy, you could also look at the rank of the matrix. Again, for for a product state, for a pure state, it has rank 1. Otherwise, it has larger rank. So you could also study what is called the Schmidt rank. So you could study the rank of rho A. Alternative. Sorry. Okay.
Go ahead, it's a personal.
Sorry. Maybe just the rank. Okay. Now the reason. Okay. So maybe I write this down here. So with the phenomenon of the reduced density matrix, we can look at the rank. The nice thing about the rank is that it generalizes to a multi-particle situation. So to a situation where we have more than just a tensor product of two factors. Because you can say the rank. The rank is the minimal thing that I need to write this pure state as a sum of tensor products. So for instance, the rank of this reduced density matrix is 2, corresponding to the fact that we cannot write this state, this EPR pair, as a single tensor product. And so you could of course now generalize this. You could ask, what is the minimum number of tensor products that I need to write a given state at, and this is called the tensor rank. So this is now closely related to the subject of entanglement, so I guess I should wrap up soon. Closely related to the topic of entanglement is correlations. But they maybe, for some it's a different concept, for others it's closely related. So we have 3 talks on the subject of correlations by Giza, by David Gross, and by Adrian Kent. Then, sorry about the boxes, which I have to label, which I use your name to label them. Now, I hope I'm yet missing one box, which is the box I want to label as random matrix theory. Just to, because I'm not an expert on this thing, maybe let me be concise. So maybe the idea is perhaps that we define all these quantities and these concepts, and you could of course ask what are their typical values? What is the typical entanglement of a quantum state? And you draw it according to some ensemble and so on. And so there's a very powerful field of mathematics, random matrix theory, which allows you to answer such questions, for certain ensembles, and so to learn about kind of typical behavior of systems in this way. So if you're Maubin, Benoit Collins, and Stanislav Jarek giving talks on this subject matter. And so finally, I promised before that I would come back to computation complexity theory. And the way I want to come back is basically via this tensor rank. So I explained before that computation complexity theory kind of arises naturally if you want to answer the question, how hard is this to compute, say, ground state? But there's also another connection, and is, for instance, via this tensor rank. Because the tensor rank, as I think we will learn in at least one of the lectures, by Peter Burgesser, by Gitan Monoly, and by John Mansberg, and I think I want to write all in alphabetical order. Perhaps, yeah, again. Actually, the tensor rank plays a crucial role in a modern approach to, in a somewhat new approach to computation complexity theory called geometric complexity theory, where it's actually important to compute tensor ranks of tensors which correspond to computational problems. So kind of for us, you could say they're important because we want to quantify entanglement. For them, they are important because they want to quantify how fast you can solve certain problems. And the amusing thing is that the methods are totally, they can be the same, right? And they can be the same. They're, in fact, intimately connected to algebraic geometry, again, in representation theory. And so I hope. I think this will be excellent. I mean, I hope this workshop will be an opportunity, for all of you to get together and talk and exchange these ideas. I hope I didn't forget anyone. There's a few names. Yes, please. Very good. Okay, so with that, I should close. Apologies for the 2 minutes delay. And I wish you all a nice conference and a happy coffee break.